this one was it?
Yeah, that looks like, yeah, that's
Okay. I thought it went up. All right. So then with the, I guess the general Hamilton's equation.
What is eta 1 and eta 2?
We're in R4.
So we're on the plane, right?
Yes, we're on plane.
So
So these are momentum in one direction, momentum in the other direction.
But what is y1?
Yes, y1, they explicitly say for this example
And
that
there is no y2?
Yeah, there is no y2 dependence.
Okay, so let's look at that function.
So then say that Hamilton's equations then take the form yj equal df.
Why do you call it y and not x? I mean, on top you had x, now it's y.
That was their example.
Okay.
They do a change of coordinates to polar coordinate later on. I think that's where part of it is. Actually, no, because they transform x too, so I'm not sure. That there, that's yj.
Oh, it is time derivative, yeah.
Yes. And then eta 1 dot equals df d1.
Negative sign.
Right, thank you. And then, of course, since we have no y2 dependence,
Right.
we then just have that eta 2 equals 0, which they then go on to say that, yes, of course, we can say that eta 2 equals some L. And they actually point out
What
that
is f? Do they write explicitly?
they do in a bit. They go through a general example, or I guess they show that we can integrate that, or I can just do the explicit one if you prefer.
No, I mean, do your thing, do as you like. I
Okay.
don't want to interfere.
All right. Yeah, so they say that the second momentum component is constant on any orbit, and we can then go ahead and so we can then write this as right. So we then pick a, I guess, level curve of the system, or integral curve. So that for some y1, eta1, eta2 equals some constant e. And then
So that's the first integral, right?
yeah.
The energy, okay.
So energy, and then we can rewrite this relation, they say, as n1 equals 5.
You also have the other one, which is eta 2. The other integral is just eta 2.
Yeah, which is eta 2 equals L. And they actually explicitly mentioned that that is one of the, essentially because we needed two conservation laws, and they refer to that as essentially one of them. From there, we can then substitute this into the first equation we have there to get y1 dot equals f of eta 1.
That's the derivative, right?
Yeah,
Okay.
and that's the partial, is equal to then y1 eta 1, which is then, as we just said, psi. And then eta 2, which is reestablished as just L. So then say that we can then find an explicit solution to that. Yeah, we can then find we can then find an implicit solution to that of fn1, y1, y1L, L inverse, and that is dy1 equals t plus c.
Capital T, just T.
Yeah, sorry. T plus c. From that, we then can, assuming that we can solve for y1, we can then, they say, go through and determine the next differential equation for eta. And from that, they then go on to give a specific example with
Well, we see that this is in quadrature solution because that gives you y1 implicitly as a function of t. And then you substitute into that equation c and you get I1, which will be, I1 is a function of c of y1 and y1 is now given implicitly, so it is another. All of this is taking inverse functions and taking one integral and that multiply.
So then they go on to define, I guess, for the still the same system in 2 dimensions. Now they switch to x and psi for some reason. Equals that's plus, yeah.
Well, let me say a word about this. Well, of course, you could immediately generalize this to n dimensions. Well, you need n integrals, right? The energy is always 1, and then you need n minus 1 others. Well, suppose that your Hamiltonian does not depend on n coordinates, which means that n minus 1 coordinates, so it only depends on 1 coordinate, or whatever that is, correct? Then n minus 1 momenta will be constant, and that will be those integrals. So if your Hamiltonian depends only on 1 coordinate, and say n momenta, then it's completely integral. Is that clear? Exactly the same logic, because you would have, but instead of just eta 2, you'll have n minus 1, which is all constant. Okay.
All right. Yeah. So they define that in, of course, we said our x's and our 2, and then immediately transform to polar coordinates. As they say, where we
So this is now, the first term is the kinetic energy, and the second is the potential energy, and that gives you the Newtonian. C is the momentum. Well, usually you would have a mass there, like c squared divided by 2m, so this is for unit mass. It's like mathematicians get the problem.
All right, yeah, so then with changing coordinates, we then rewrite this equals
Why they want to use polar coordinates is because your potential only depends on the absolute value, so it depends on radial coordinate. So your Hamiltonian depends on the 1 coordinate, and that's why, as I told you, if Hamiltonian depends on the 1 coordinate, it's completely integral. You better choose that function, that coordinate is one of them. You change your coordinate. Here it has 3 coordinates, right? But V depends only on 1 coordinate, namely the radial coordinate. So you change your coordinate so that it only this is 1 coordinate, and then 2 other coordinates will be constant.
all right. So now that we have this set up, we can then write the first pair of
Excuse
ODEs.
me, what is it? Is it y1 to negative 2?
Yes.
Where does this come from?
I believe that comes from when you change the. Yeah, I think it's just coming from when changing the metric. I could be wrong.
Let's see.
Because this comes from the angular momentum, right? This whole general term.
Oh, it is eta 2 squared.
Oh, thank you.
Eta 2 squared. y1